Thanks everyone for taking the time out and joining. I'm actually tuning in from Vancouver, where I just presented Multinet yesterday at ICML. It's really nice to see a lot of people stoked about what we're working on, and so I'm excited to share more with all of you. I have spoken about Multinet in the past CRCs, and there's a lot of talks we've given, but I'm sure there are new folks here who haven't heard a lot about Multinet, so I'll give a brief overview and then jump into the details. So I've been leading Multinet for around a year now, and I work with some really talented researchers, some of whom you'll hear from later today. So Locke, Deb, Harsh, and we have two new, also very talented researchers, Sean and Riddle, joining the team. Excited to scale up the project and you know take Multinet to the moon. So just a brief overview of like what Multinet is and why we do it. So Multinet is kind of inspired by our thesis that today's generation of AI systems are really good at multimodal understanding, but we think that the next phase of AI systems become systems that actually take actions and become really useful. And for that, they have to have a native understanding of what an action is, and it isn't limited to just function calling, which is the limit of like AI tool use today. And a key direction for that is having good benchmarks that measure the multimodal understanding ability as well as the action taking capability of these models and systems. And you know, all the benchmarks that are currently there in today's like AI community, they're pretty specific and they evaluate certain things. And we want to have like one-stop shop where we can evaluate a model or a system on both its understanding capability, its action taking capability, and what makes it a really good generalist foundation model. And so the goal with Multinet is to build, probably the largest open source vision language and control eval dataset that we can benchmark these models on, have clearly well-defined metrics that kind of capture how well these models do on all these different tasks, domains, environments. And also, obviously, the biggest goal is to enable everyone in the community to use this. So an easy to use like software toolkit, which we already do have to kind of access and standardize the data. Standardization becomes important, especially in control when you have data sets from a variety of different sources, all these different formats, some that haven't even been maintained for years now. So I think that's a key contribution, makes it easier for everyone to use the data. And then obviously we want this to be a very challenging benchmark. To assess how good these generalist foundation models are today. There are like vision language models today that everyone knows about, and there's a new emerging class that's like rapidly growing vision language action models, which are basically VLMs that are fine-tuned or pre-trained. Sometimes it's like architectural modifications to work on robotics datasets. So that's kind of the goal with Multinet. We already do have a version of this. We have a lot of work that we've done that's already open source. I'm sure we'll share the slides with you soon, so you can check out the website and our dataset spec paper. The two major releases we've had so far, we called it like V0.1, V0.2. With V0.1, basically our goal was, take these state-of-the-art VLAs and VLMs and kind of like evaluate them on how they do on real-world robotics data. Now for VLAs, this is a slight distribution shift in their training data. But for VLMs, of course, it's a massive jump. They're not really trained on offline trajectories of real-world robotics. And so we want to see how well do they do, how well do models that are good at multimodal understanding adapt to action taking, and how well do models that are good at action taking, how well do they do on like a slightly different distribution of data. So we kind of curated this list of data sets from the OpenX embodiment collection, which is like this large effort that consolidates real-world robotics data across different embodiments, tasks, environments from a variety of universities. And a few of these, as you can see, are within training for a model like OpenVLA. And this is important because you get to see how well these models do on the data that they've been trained on and on data sets that are unseen but are very similar to the data that they've been trained on. So one thing that we notice is that overall performance is really bad. Like all of these models do not generalize well, even if the data distribution shift is minor or major in the case of VLMs. And one interesting thing is that on unseen data, VLAs have very inconsistent performance. So the performance is highly dependent on what kind of embodiments, what kind of tasks, what kind of environments. And and for VLMs, we developed this framework called Genesis, which basically allows you to adapt these vision language models to a completely different domain, which is action taking, which Dip and one of our alumni, Kyle, worked on as well. So V0.2, what we did was we shifted the data distribution even further, and we said, okay, let's take the state-of-the-art VLMs and VLAs and evaluate them on 2D procedurally generated gameplay data. Now, gameplay data is very rich in action. You have visual observation, and you have a final goal, and you take intermediate actions to like reach this goal. And in the case of for V0.2, the data set we picked was ProcGen. ProcGen was an environment that OpenAI created, part of their GYM ecosystem, but we are evaluating it on offline trajectories of expert, agents that are experts in ProcGen, similar to offline trajectories that we did in robotics. So we found a lot of interesting results with this. This is just a snapshot of what the ProcGen data looks like. I'm sure a lot of you have played some of these games at some point in your life as well. So the action space for all of these games are discrete, and they correspond to like button presses or no operations. And so it's a discrete action space and mutually exclusive action classes. You can only hit one button to take one action at a given time step. Next slide, please. Yeah. So because this is a discrete action space, we had to get a little more innovative with the evaluation metrics compared to just using a mean square error in V0.1. And so we use a Breyer mean absolute error, which basically assesses how confident these models are at predicting the the right action class in the discrete action space. And then precision recall F1 are standard, but we went with both the micro and macro versions because macro helps kind of alleviate the issues with respect to overrepresented classes. And then invalid percentage is basically saying, okay, can these models even predict outputs in the right format? How badly do they struggle? And yeah, these are the models that we evaluated for V0.2. All state of the art. Pi0 is a generalist robotics policy by a company called Physical Intelligence. Pi0 with FAST is a new kind of tokenizer that they add to their base model. OpenVLA, same as the model we evaluated in V0.1, and then obviously GPT-4 and 4.1 state of the art VLMs. So basically, we found that they perform really, really badly. So VLMs are not able to adapt to this whole like new domain of like action data, and VLAs also struggle a lot when it goes from real world robotics to gameplay data. So there's not a lot of transfer even within the action domain. So the maximum possible Breyer error is 2, and you'll see that most of these models that errors kind of like almost reach that limit, so they struggle a lot. Even the invalid percentages, you'll see that some of them around 80%. So architecturally and the way they've been trained and their output processing methods don't really allow them to even generalize to like domains such as like this one. And recall is very bad as well. So overall performance really bad. Very hard to generalize given the current state of architectural design, input processing, output processing, training methods. Very insightful, especially when with our goal for Multinet to build these like generalist like benchmarks that assess how good foundation models are across all these different modalities and tasks. So one interesting result in V0.2 that I want to just highlight, this is all, you can read more about it in our paper, our website. It's all on the website. This one is interesting because it kind of like showed us how the architecture of these models influence the results. So what this is basically the frequency of these models predicting a certain action class within the discrete action space, right? So the action space is 0 to 12, and how often do they predict a certain class when the ground truth is a certain class? And one thing we saw is that the autoregressive models, which are the GPT-4o, 4.1, OpenVLA, and the Pi0 with the fast tokenizer. First of all, there's a phenomenon where when they are evaluated in data that is unseen, and if it's a discrete action space, the predictions kind of collapse to one or maybe 1 to 3 action classes. And they're not necessarily the right action class. It's most often the wrong one. But they collapse and concentrate, and you can see like kind of like the darker vertical lines that show the concentration of their predictions. And one interesting thing is that with autoregressive models, you'll see that this action class collapse is highly concentrated. But for pi zero base, which is a diffusion based model, you'll see that the predictions are kind of like distributed. And this kind of goes back to, again, like how they're built. Autoregressive models are forced to predict a specific action class because they're softmax at the end during their inference. But with diffusion models, they're basically trying to model how their training data looks. And they're trying to say, hey, like, this is what we were trained on, and this is new unseen data. How close can we get it to what we've seen in the training data? So their predictions are very distributed, diffused, and you can see it very clearly in this confusion matrix. So this is a very interesting result and informs us about how we want to build these models as we go forward. Yeah, so a lot of exciting things coming up with Multinet. So right now, we're kind of revamping our dataset coverage for Multinet because the AI space moves rapidly. There's a lot of new exciting datasets. We want to have very challenging evaluation specific datasets and not focus too much on, the pre-training data. And we want to have like, very well designed software toolkits for submissions and evaluation harnesses so that the community can engage easily, more people can use it, more people can evaluate their models. And obviously want to continue like profiling these state-of-the-art VLMs, VLAs, generalist models, zero shot on our data sets. And we do want to engage more with the community, especially the model providers, and have them actively collaborate with us and like, evaluate their models when they release their models on Multinet. And longer term, so far we've done, offline trajectories and zero shot. We do want to get into few shot evaluations, fine-tuned evaluations, and also, like we want to eventually get to like online environments where these models are kind of evaluated in a live setting and get feedback for every action they take. And also we want to make it a live benchmark, similar to live bench, where we're continually updating it, ensuring that it is a contamination-free benchmark, and just to make sure that none of the new models have been trained on the data that we're evaluating them on. And yeah, so a lot of exciting stuff. We're scaling up the team, we're scaling up the efforts. If you're interested, next slide, please. I think, yeah, it shows everyone how you can reach out to us. Feel free to drop any feedback, thoughts, reach out to us if you want to contribute, collaborate. All of us, me, Deb, Locke, Harsh, Sean, and Mridil. And so, yeah, that's it from Multinet. Thanks, guys.